Hello again. In the previous video, we discussed how you can define and use functors to help define our fecundity phenotype. Just to review, we are still specifying our genotype-phenotype maps. Here, we'll look at the second phenotype we are simulating, namely, a phenotype controlling individual survivorship. Now recall that when we defined our tuple for use in calculating the fecundity phenotype, we only used vectors that came with our ins class, namely, the genotype vectors and the phenotype vector into which we will store the result of our calculations. So as before, we'll create a functor that we'll define as a struct. Let's call this functor mortality calculator. We'll once again have an operator that performs the main calculations and instruct a functor that we need to be able to execute this on the GPU and provide a template for the tuples. Now in the fecundity example, we use tuples as the input for our functor, but often we might want to have other kinds of input for our functors. For instance, rather than the genotype-phenotype map that looks something like this, we might want a genotype-phenotype map that looks something like this, where C sub I represents an arbitrary coefficient that weighs the allelic effects. Here's where the second type of input to our functors come in. Occasionally, we might want to specify arguments when we construct our functor that are not represented by tuples. I'll refer you to the SPEGG documentation for other reasons why this might be. So we'll need to create references to these other input arguments inside our functor structure. One of the things that makes SPEGG an effective framework for parallelization is that each replicate of our simulation is represented by a patch, and each patch can have its own coefficient in this equation. This allows us to simulate the model in parallel across a gradient of coefficient values. So in the example of a genotype-phenotype map, you can imagine that you have variables, such as the genotypic and phenotype values that characterize an individual, as being elements of a tuple, but the parameters governing the genetic architecture of the traits, such as the constant we just looked at, as being separate input values that are not represented using tuples. So suppose we are testing how varying the coefficient value C in the genotype-phenotype map affects our results. The way SPEGG does this will be each patch would therefore have its own value for C, so our approach ends up looking something like this. In SPEGG, we can specify a vector that represents the different values of this constant for different patches. What we'll do is therefore declare pointers to arrays for these latter types of variables. Now we can specify the mortality calculator functor as depending on these input variables and map the input variables to the pointers we just declared. Once we've recast things in this way, let's look at how we define our operator. Notice that we want the constant used for calculating any individual's genotype-phenotype map to be specific to the patch that that individual inhabits. So if we declare calculate phenotype and define it in the .cu file, one of the elements of the tuple will be the individual's patch. So back to our functor definition. To make things readable, let's go ahead and declare a variable that stores this individual's DEEM. Now if the individual inhabits patch P, then we need to use the pth element of the allelic effect vector to determine this individual's phenotype. We'll access that constant and then calculate the genotype-phenotype map using the thrust get operation for the remaining elements of our tuple. And that's how we define our mortality functor. Now just as we defined the calculate phenotype function for the genotype-phenotype map for the fecundity phenotype, we need to write the code for a calculate phenotype function for the mortality phenotype. Because the base genotype-phenotype map class used virtual functions, notice that we can use the same interface to the calculate phenotype function. Let's review this calculate phenotype function. We use the for each function from thrust, create and zip our tuples using the first and last elements of our vectors, and then call our functor on these tuples. This operation will then execute our functor in parallel on the GPU. We're going to adopt a very similar approach for the calculate phenotype function associated with the mortality phenotype. But unlike the functor associated with fecundity discussed in our previous demonstration video, our functor now has a second form of input, namely, the vector of constants used for calculating the genotype-phenotype map for each individual that we need to access when we call the functor. The vector of constants that vary by patch is going to be stored in our parameters class. We can access it by calling the function getVectorPointer from the parameters class. Just very briefly, the constants will be stored in an input file that will be read into the parameters class. A later video will discuss how to configure that input file. Finally, to make this vector available to our functor, we need to have a pointer to it. We're going to use a CUDA function called rawPointerCast and then specify the pointer to our vector of constants. Again, we use the forEach function from thrust and create tuples. But recall in our functor definition, we needed to access the individual's patch. So the first element of our tuple will be the patch of the affected individuals. The remaining elements of the tuple are these individuals' genotypes and phenotypes. We declare a corresponding tuple for the final elements. Now we set up our functor using this pointer as an argument. It's important to always set up the functor like this whenever we're passing it arguments that aren't just tuples. Once we've done that, we can write the code that uses this functor. Finally, we can call our functor. Notice that we aren't going to use parentheses this time when we call our functor inside thrust forEach. Instead, we just call the local name of the functor that we set up. So, we've defined both our mortality and fecundity phenotypes, and done so in slightly different ways. There are other examples in the SPEGG documentation too, where we go over how to make your custom functors in some depth. Now that we've defined our genotype-phenotype maps, let's call them in a way that our demo species object can access them. If we go back to the .cu file associated with the demo species object, the setPhenotype involves what is called a factory method, create genotype-phenotype map, that will actually create a genotype-phenotype map object. So let's spell this out inside the genotype-phenotype map template.cu file. This file is located in Add Kids, and if we open it, there are a lot of commented out placeholders. Since we have now defined our species-specific genotype-phenotype maps, we can reference the header file that contains them. We can also populate our create genotype-phenotype map function. Notice that one of the arguments is phenotype index. We can therefore create a series of conditionals to return the correct genotype-phenotype map object for the corresponding phenotype index. The indices associated with each phenotype are defined in your input file and are stored inside a vector called species-specific values inside the patch parameters associated with your species object. This functionality is implemented in the base class from which our class, DemoSpecies, derives. So our conditionals will simply check which of our phenotypes the phenotype index supplied by the create genotype-phenotype map factory corresponds to and return the appropriate genotype-phenotype map class. We save our changes, and then we're done. I should note that this particular interface might be simplified and automated in the future. We've now completely specified the initialization for demo species. In the next two videos, we'll go over the functionality for adding new individuals to our species object. Thank you again for watching, and if you have any questions, shoot me an email via our mailing list, speg-users@googlegroups.com.